So, if you look up at the night sky tonight, you might feel like you are seeing the universe in all its vast, shining glory.
Right, the glowing nebulas, the stars.
Exactly. You might think that the sweeping arm of the Milky Way, all of that represents the cosmos, but it doesn't.
Not even close.
No, not even close. You are looking at a rounding error, because almost everything out there is entirely invisible.
Yeah, it's quite humbling when you really think about it.
It really is. So, welcome to this custom-tailored deep dive into the unknown. Today, we're setting out on a very quiet, contemplative exploration of the unseen forces that are, well, silently pulling the strings of reality. We're going to explore what cosmologists call the dark universe.
Which forces a complete shift in perspective, right? Because our entire human experience, everything we know, is built around things that emit or reflect light.
Yeah, things we can actually see.
Exactly. Yet, when we step back and look at the actual architecture of space, the light is practically irrelevant. I mean, we are living in a shadow realm. We're utterly dependent on this massive, invisible framework that essentially dictates the life and death of every galaxy.
Including our own.
Including our own, yeah.
So the mission of this deep dive is to map that invisible framework. We're confronting the staggering reality that 95% of everything around us is completely unknown.
95%. It's a staggering number.
It is, and we will chart the history of this revelation, tracking the slow, agonizing realization that something is just fundamentally missing from our equations.
Breadcrumbs left by anomalous galaxy clusters.
Yes, and we'll trace the cosmic tug-of-war between two invisible titans, dark matter and dark energy, and we'll seek out the profound, sometimes desperate insights of giants like Albert Einstein and Stephen Hawking, who really tried to peer into that dark void.
And we have a phenomenal stack of sources to guide this journey today.
We really do. We're looking at detailed NASA cosmological briefings, Nobel Prize Committee press releases, some newly translated historical analyses of Einstein's forgotten 1931 papers, and Stephen Hawking's absolute final theories on the multiverse.
It's a lot of ground to cover.
It is. But before we step off the edge of the visible map, I want to warmly invite you to subscribe and like to this channel, Decoding of the Dark, so we can continue this relaxing, awe-inspiring journey through the mysteries of space together. Okay, let's unpack this as we transition out of the comfortable illuminated world and drift into the vast, beautiful, unknown dark.
So, to truly anchor ourselves in the scale of this mystery, we really have to start with the most accurate inventory of reality humanity has ever compiled.
Right.
And this inventory comes primarily from the European Space Agency's Planck mission.
Okay.
Planck was a space observatory, and it was designed to map the cosmic microwave background. That's the very oldest light in the universe.
Yeah.
The fading afterglow of the Big Bang itself.
The ultimate baby picture of the universe.
Exactly. And by studying the microscopic temperature fluctuations in that ancient light, cosmologists were able to essentially weigh the different components of the universe. And the results were, well, incredibly humbling.
Yeah, I bet.
Roughly 5% of the universe is made of what we call normal matter.
5%. And we really need to define normal here, because in a cosmic sense, it's actually the ultimate anomaly, right?
Yeah, it really is.
When we say normal matter or baryonic matter, we mean absolutely everything humanity has ever interacted with. Protons, neutrons, electrons.
Every star that has ever ignited.
Yeah, every rogue planet drifting through the void, every swirling cloud of interstellar dust. I mean, it's the device playing this audio, and it is your own physical body.
Yes.
The defining characteristic of this 5% is that it interacts with the electromagnetic spectrum. It emits light, it absorbs it, or it bounces light back into our eyes. It is a visible universe. And that's it. 5%.
Which leaves a staggering 95% of reality totally unaccounted for by anything we can see or touch.
Right.
The Planck data breaks that invisible portion down into two distinct categories. So about 27% of the universe is dark matter and 68% is dark energy.
Okay, 27 and 68.
Yeah, and it is vital to understand that these are two fundamentally opposing phenomena. They are locked in a cosmic struggle.
How so?
Well, dark matter acts as the gravitational glue of the cosmos. It pulls things together. It provides the heavy, the invisible scaffolding necessary for gas to clump together and ignite into stars, and for those stars to gather into galaxies.
So it's the builder.
Exactly. But dark energy acts as the great repulsor. It is the engine driving the accelerated expansion of the universe, actively pushing the fabric of space apart.
So we have the glue trying to hold the cosmos together and the engine trying to tear it all apart. And we, sitting here in our little 5% sliver of baryonic matter, are just along for the ride.
We really are. If we connect this to the bigger picture, the philosophical weight of it is just immense. I mean, every scientific revolution in human history, from the invention of the wheel to splitting the atom, from Galileo to sequencing the human genome, all of it has been entirely restricted to studying just 5% of existence.
Wow.
We are a minor impurity floating in a dark ocean. But I should also clarify that the term dark is a bit of a misnomer. It's a historical accident of naming.
Because it makes people think of like a black cloud.
Right.
Or an ominous shadow blocking the stars behind it.
Which is entirely the wrong way to visualize it.
Yeah.
It is not a color. It is not a shadow. A much more accurate term would be transparent or invisible matter.
It's invisible matter. Okay.
We call it dark solely because it completely ignores the electromagnetic spectrum. If a photon of light hits a cloud of dark matter, the photon doesn't bounce off, it doesn't get absorbed, and it doesn't get scattered. The light passes straight through as if the dark matter isn't even there. It does not interact with light in any way whatsoever.
To put a picture to this, imagine you have a large, heavy glass jar sitting on a table, and it's filled with exactly 100 jelly beans.
Okay, I like this.
You look closely, and you can only see 5 standard, brightly colored jelly beans resting at the very bottom. Those are your visible baryonic matter. But when you pick up the jar, you struggle to lift it because it feels incredibly dense.
Right, because of the dark matter.
Exactly. That's because there are 27 completely invisible jelly beans in there. You can't shine a flashlight on them to reveal their shape, and you can't reach in and feel them because your hand would pass right through them. But you can undeniably feel their weight, their gravitational pull on the jar.
Yeah.
But here is where the analogy breaks your brain. Because there are also 68 other invisible jelly beans in the jar, and these ones aren't just sitting there, they are somehow pushing against the glass, causing the jar itself to steadily expand in your hands.
That is a brilliant way to conceptualize the cosmic budget. The weight of the jar represents the dark matter, and the expanding glass is the dark energy.
But I have to push back here.
Okay, go for it.
And I guarantee anyone listening, lying under the stars thinking about this, is asking the exact same question. If we absolutely cannot see it, touch it, smell it, or interact with it in any physical way other than gravity, how can we be so incredibly sure it's actually there?
It's a fair question.
Aren't we just inventing invisible jelly beans to save our own broken theories? Like, if our math for gravity says a galaxy should fly apart, but the galaxy is clearly holding together, why is the default assumption there must be invisible magic matter everywhere, rather than our math for gravity is wrong?
You know, this skepticism is incredibly healthy. And honestly, it is the exact skepticism that drove the astronomical community for decades. No one wanted to invent invisible matter.
Does it sound crazy?
It does. Science is inherently conservative. It resists adding new, unseen entities unless the evidence becomes utterly overwhelming. To understand why cosmologists were backed into a corner and forced to accept dark matter, we have to trace the historical breadcrumbs. We have to go back to the 1930s.
Okay, let's go.
To a brilliant, famously abrasive Swiss-American astronomer named Fritz Zwicky.
Zwicky is a legend.
Okay.
Mostly because he had a habit of calling his colleagues spherical bastards.
Yes.
Meaning they were bastards no matter which direction you looked at them.
He was quite a character.
Yeah.
But in 1933, he was working at Caltech and pointing his instruments at the Coma Cluster. Now, the Coma Cluster is a monstrous gathering of over 1,000 individual galaxies bound together by gravity, sitting roughly 300 million light years away from Earth.
That is massive.
It is. And Zwicky wasn't just taking pretty pictures. He was measuring the velocities of these individual galaxies to see how they moved within the swarm.
How do you even measure that?
He was utilizing the Doppler effect. Just as the pitch of a police siren changes as it moves toward or away from you, the wavelength of light from a galaxy shifts based on its motion.
Correct.
So if a galaxy in the cluster is moving toward us, its light compresses and shifts toward the blue end of the spectrum. If it moves away, the light stretches and shifts toward the red end. By meticulously measuring these microscopic shifts in the spectral lines of the galaxies, Zwicky calculated how fast they were zipping around the center of the Coma Cluster.
And the numbers were absurd.
They were terrifyingly high. The galaxies were moving at incredibly high velocities, some upwards of 2% the speed of light.
2% the speed of light.
Yeah.
Wow.
And to understand why this was a problem, we need to quickly review the physics of orbits. which rely on the inverse square law of gravity.
Right. Gravity weakens exponentially with distance. If you move twice as far away from a star, gravity isn't half as strong, it's 4 times weaker.
Correct. The only thing that prevents a fast-moving object from flying off into deep space is the gravitational pull of the mass it is orbiting.
Like a ball on a string.
Exactly. If you swing a heavy ball around your head on a string, the string provides the inward force.
Yeah.
If you spin it too fast, the force exceeds the strength of the string snaps, and the ball flies through the window.
Yeah.
In a galaxy cluster, the collective gravity of all the stars and gas is the string. So Zwicky calculated the total visible mass of the Coma cluster by measuring all the starlight it emitted. He then calculated how much gravity that visible mass could generate.
And the math failed spectacularly.
Completely. The string of gravity generated by the visible stars was nowhere near strong enough to hold onto galaxies moving that quickly. Based on the visible light, the Coma cluster should have flung itself apart billions of years ago.
But it hadn't.
No, yet there it was, calmly sitting in the telescope lens, completely stable. Zwicky estimated that to hold the cluster together at those speeds, there had to be 400 times more mass than what he could see.
400 times.
Yes, he coined a phrase in his paper, dunkel materie, dark matter.
He threw down the gauntlet. He essentially said, hey everyone, 99% of the universe is missing. And the astronomical community's response was profound silence. They basically ignored him for 40 years.
They did. And looking back, it's easy to paint the community as foolish, but they had very valid, data-driven reasons to dismiss his claims.
Oh, really? Like what?
Well, in the 1930s, cosmology was a messy frontier. For one, the Hubble constant, the metric used to calculate cosmic distances, was drastically miscalculated at the time. This error cascaded through all equations, making the universe appear only about 2 billion years old.
But we knew it was older than that.
Exactly. Geologists already knew the Earth's crust was older than 2 billion years, so physicists knew the baseline cosmological numbers were deeply flawed. If the distance to the Coma cluster was wrong, Zwicky's velocity and mass calculations were fundamentally suspect.
Okay, that makes sense. On top of that, Zwicky made a rather sweeping assumption about the stars themselves, didn't he?
He had to. He assumed that the overall mass-to-light ratio of the galaxies in the Coma cluster was similar to our local neighborhood around the Sun. But as astrophysics matured, we learned that galactic light is utterly dominated by massive, incredibly bright, hot blue stars.
They outshine everything else?
They do. They put out a disproportionate amount of light compared to their mass. When you correct for this, the visible matter actually accounts for significantly more mass than Zwicky thought.
Ah, I see.
The discrepancy wasn't a factor of 400. With modern measurements, we know the missing mass in the Coma cluster is closer to a factor of 6.
Still a lot, but not 400.
Right. So between the distance errors, the stellar mass errors, and Zwicky's famously combative personality, the community easily filed dunkel materie away as an observational error.
So the Phantom Menace goes back to sleep until the 1970s. And this is where the story shifts from giant clusters of galaxies down to the individual pinwheels. Enter Vera Rubin and Kent Ford.
Yes. Vera Rubin's work is a masterclass in meticulous, undeniable observation. By the 1970s, observational technology had leaped forward. Kent Ford, a brilliant instrument maker, had developed a highly sensitive image tube spectrograph. It could measure the subtle red and blue shifts of light with unprecedented precision.
And Rubin wanted to use it.
She did. But Rubin didn't want to look at chaotic, messy clusters like Zwicky did. She wanted clean, simple data. So she pointed Ford's spectrograph at the Andromeda Galaxy, our nearest large spiral neighbor.
Let's visualize a spiral galaxy to understand her experiment. It looks like a giant, glowing cosmic pinwheel. You have a dense, incredibly bright bulge of stars in the very center, and then these wispy spiral arms of gas and stars sweeping outward into the dark.
A beautiful structure.
Yeah. And Rubin wanted to map the rotation curve of the galaxy. She wanted to measure exactly how fast the stars were orbiting the center at different distances.
And standard Newtonian physics made a very clear prediction about what she would find. It's the exact same gravitational principle that governs our solar system, often called a Keplerian decline.
How does that work?
In our solar system, 99.8% of the mass is concentrated in the sun. Because gravity weakens with distance, the planets closest to the sun experience the strongest pull, so they must orbit incredibly fast to avoid falling in. Mercury zips around the sun at almost 30 miles per second.
Wow.
But way out in the freezing dark, Neptune experiences a very weak gravitational pull. Therefore, Neptune orbits very slowly, only about 3 miles per second. If Neptune orbited at Mercury's speed, the sun's weak gravity couldn't hold it, and it would fly off into interstellar space.
So Rubin applies this logic to Andromeda. The vast majority of a galaxy's visible light, and therefore presumably its mass, is heavily concentrated in that glowing central bulge.
Exactly.
The outer spiral arms are dim and sparse. Therefore, the stars out on the far edges of the galaxy should be orbiting much slower than the stars near the center. The rotation curve should go down like a playground slide the further out you look.
But that is not what the spectrograph revealed. As Rubin measured the velocities of stars and gas clouds further and further from the galactic core, the orbital speeds did not drop off. They stayed fast.
Wait, really?
Yeah. She discovered what are now famous as flat rotation curves. A star situated way out on the dim, sparse, absolute outer edge of the galaxy was zipping through space just as fast as a star deep in the dense, bright center.
This is the moment the universe broke Newtonian physics. Based on all the starlight, based on every atom of gas we could see, those outer stars are moving entirely too fast. The visible gravity of the galaxy was completely insufficient. Those stars should have been flung out of Andromeda like sparks off a grinding wheel.
The implications were unavoidable. Rubin accumulated data on dozens of spiral galaxies, and the result was always the same: flat rotation curve.
Every single one.
Every one. The only logical explanation, the only way to save the laws of gravity, was to conclude that the visible galaxy, the glowing pinwheel we see in telescopes, is just a tiny luminous core embedded deep within a gigantic, invisible sphere of mass. This dark matter halo extends hundreds of thousands of light years beyond the visible edge of the galaxy, providing the immense gravitational grip required to keep those fast-moving outer stars locked in orbit.
It's incredible to think about the human element here, too. Rubin was doing this groundbreaking work while fighting blatant sexism. In the mid-20th century, women were often barred from using the major observatories.
Yes, she faced tremendous hurdles.
She had to fight just to get time on the telescopes. And when she presented her flawless data, the community still dragged its feet. They didn't want to accept that the universe was filled with invisible halos, but her data was bulletproof. It couldn't be ignored like Swicky's.
It is the ultimate triumph of the scientific method. The data dictates reality, regardless of our prejudices. And today, we don't just rely on the spinning speeds of galaxies. We can literally see the structural footprint of dark matter through a phenomenon called gravitational lensing.
Oh, let's unpack the mechanism of gravitational lensing because it sounds like science fiction. Einstein's theory of general relativity tells us that mass doesn't just pull on things, it actually bends the fabric of space-time itself. The heavier the object, the deeper the dent it makes in space-time.
Precisely. Or rather, that is a highly accurate way to frame it. When light travels across the universe, it travels in a straight line through space. But if space itself is curved by a massive object, the light's path bends, following the curvature.
Like a bowling ball on a trampoline.
Exactly. Imagine a bowling ball resting on a trampoline, creating a deep dip.
Yeah.
If you roll a marble across the trampoline, its path will curve as it passes the dip. Now imagine a massive galaxy cluster acting as the bowling ball, and the light from a galaxy far, far behind it acting as the marble.
So when we point the James Webb Space Telescope at a distant cluster, we aren't just seeing the cluster, we are seeing the light from galaxies billions of light years behind it. But because the cluster is warping space-time, that background light gets bent, magnified, and smeared into these weird funhouse mirror streaks and arcs.
Yeah.
It's like looking at a candle flame through the thick base of a warped wine glass.
And here's the genius part. Astronomers can measure the exact angle and distortion of those smeared light arcs. By reverse engineering the optics, they can calculate exactly how much mass is required to warp space-time to that specific degree.
And what do they find?
When they do this, they find that the visible galaxies in the cluster only account for a tiny fraction of the necessary mass. The vast majority of the space-time warping is being caused by massive, invisible clouds of dark matter surrounding the cluster. We can literally draw 3D maps of dark matter by observing how it distorts the light of the visible universe behind it.
Okay, so the gravitational footprint is undeniable. It's spinning our galaxies, it's holding our clusters together, it's warping the fabric of space. But this brings us to the agonizing roadblock of modern physics.
The big question.
Yes, we know exactly what dark matter does, but we still have absolutely no idea what it is. We are surrounded by it, it's dictating our cosmic destiny, and we can't catch a single piece of it. If it's not protons and neutrons, What are these invisible jelly beans made of?
That is the multi-billion-dollar question.
Oh.
For decades, the dominant theoretical candidates have been hypothetical subatomic particles.
Okay.
The most famous class is WIMPs, weakly interacting massive particles. The theoretical framework suggests these are particles forged in the Big Bang that possess significant mass, meaning they exert gravity, but they do not interact with the electromagnetic force or the strong nuclear force. They only interact via gravity and the weak nuclear force.
Which means they can literally pass through solid matter. A WIMP could be passing through my hand right now, and because its electromagnetic field doesn't repel the electromagnetic field of the atoms in my hand, it just ghosts right through.
Exactly. But physicists theorize that if two WIMPs were to collide directly with one another, they might annihilate, releasing a faint flash of gamma radiation. So, we have specialized telescopes staring at the dense core of the Milky Way, hoping to see an unexplained excess of gamma rays that might be the spark of colliding dark matter particles.
But WIMPs aren't the only ghost particle on the whiteboard. There are also axions. And the origin story of the axion is a great example of how weird theoretical physics can get.
Axions are fascinating because they weren't invented to solve the dark matter problem. They were hypothesized in the late 1970s to solve a completely different, highly technical issue in quantum mechanics known as the strong CP problem.
Let's break down the strong CP problem for a listener who doesn't have a PhD in quantum chromodynamics.
Let's try. In physics, there is a deep love for symmetry. We expect the laws of physics to behave the same way even if you swap certain properties. For example, if you take a physical process, swap all the particles with antimatter particles, that's charge symmetry, and flip the spatial coordinates, like looking in a mirror. Parity symmetry. The strong nuclear force, the force holding the nucleus of an atom together, should behave identically.
Okay, so a perfect mirror image.
Right. The math of the standard model says there should be a slight violation of this symmetry, a subtle imbalance. But when we run the experiments, we find no violation at all. The strong force preserves this perfect symmetry, and the math couldn't explain why.
It's like finding out a weighted coin still lands on heads exactly 50% of the time, and it's driving the mathematicians crazy.
That's a great way to put it. So to fix the math, physicists Roberto Pache and Helen Quinn proposed a new, invisible field permeating the universe that naturally cancels out that imbalance. A byproduct of this field is a particle called the axion.
And what's special about it?
An axion would have an incredibly tiny mass, billions of times lighter than an electron, and practically zero energy. For a long time, it was just a mathematical band-aid. But then cosmologists realized that if the Big Bang produced a truly astronomical number of these ghostly low-mass axions, they could collectively provide the missing gravity of the universe. They would flow through space like an invisible, frictionless fluid.
It's an elegant solution, but there is a totally different non-particle theory that I find deeply unsettling, mostly because it ties back to Stephen Hawking. What if dark matter isn't a swarm of new exotic subatomic particles, but rather an ancient swarm of black holes?
Ah, primordial black holes. This is a brilliant concept. When we typically visualize a black hole, we think of stellar death. A massive star burns through its nuclear fuel, the outward pressure of fusion stops, and gravity crushes the core into a singularity.
Right.
But a primordial black hole is different. Hawking theorized about the state of the universe fractions of a second after the Big Bang. The universe wasn't a vacuum. It was an unimaginably hot, dense plasma.
And it wasn't perfectly smooth. There were quantum ripples.
Yes, microscopic density fluctuations. Hawking calculated that if a particular pocket of this primordial plasma was just slightly denser than the surrounding area, the intense pressure and gravity of the early universe could crush that pocket directly into a black hole, bypassing the need for a star entirely.
Wow.
These primordial black holes would have formed before the first atoms even existed.
Which means they could be any size. A stellar black hole has to be massive because it's made from a star. But a primordial one formed from a dense pocket of plasma could be microscopic.
Absolutely. A primordial black hole could be the size of a single atom, yet contain the mass of a large asteroid. Or it could be the size of a golf ball and weigh as much as the Earth.
That is terrifying.
And because they are black holes, they emit no light. They're perfectly dark. They would just drift blindly through the cosmos, exerting a gravitational pull. Some theoretical models suggest that dark matter halos aren't clouds of axions or WIMPs, but rather vast ancient swarms of these primordial black holes drifting through the galaxy.
I read about that.
Yeah, there are even recent papers suggesting a tiny primordial black hole might pass through the outer edges of our solar system every few decades, causing microscopic orbital perturbations.
Okay, we've laid out the magnificent theories. WIMPs, axions, microscopic black holes. But we have to be intellectually honest with ourselves and with the listener right now. Humanity has spent the last 40 years building massive, billion-dollar detectors.
We have.
We've buried giant vats of liquid xenon deep inside mountains to shield them from cosmic rays, cooling them to near absolute zero, waiting in the pitch black for a single WIMP or axion to accidentally bump into a normal atom and create a tiny flash of light. And after decades of searching, absolute silence, we have found nothing. Zero conclusive physical evidence of a dark matter particle.
Which brings us to the great heresy of modern cosmology. The scientific method demands that if an experiment continually fails to find what a theory predicts, you must question the theory itself.
Are we repeating the mistake of the planet Vulcan? Back in the 19th century, astronomers noticed the orbit of Mercury was wobbling in a way Newtonian gravity couldn't explain. So they assumed there had to be an invisible planet hiding near the sun, tugging on Mercury.
They even named it Vulcan.
Exactly, but Vulcan didn't exist. Newtonian gravity was just fundamentally incomplete at high masses. Once Einstein came along with general relativity, Mercury's wobbly orbit made perfect mathematical sense without needing an invisible planet. Are we doing the same thing today? Is dark matter our generation's Vulcan?
This represents one of the most intense, slow-burning debates in modern astrophysics. The alternative to inventing invisible matter is to assume our math for gravity is incomplete. The leading theory for this is MOND, modified Newtonian dynamics, or Milgromian dynamics, proposed by Mordechai Milgram in 1983.
Let's explore the mechanism of MOND. How does it change the rules?
MOND takes aim directly at the extremes. Newton's inverse square law of gravity works perfectly well on Earth, and it works perfectly well in our solar system. But Milgram proposed that when you scale up to the size of a galaxy and you look at the extreme outer edges, where the gravitational acceleration becomes unimaginably weak, an acceleration millions of times weaker than what we feel on Earth, gravity stops following the inverse square law.
It changes its behavior.
Yes. MOND proposes a fundamental threshold called a knot. Once the gravitational acceleration drops below this incredibly low threshold, gravity weakens at a much slower linear rate rather than an exponential rate.
Okay.
If you apply this tiny mathematical tweak to the laws of gravity, a miraculous thing happens. You can perfectly predict the flat rotation curves of the spiral galaxies Vera Rubin observed.
Really?
Yes. The outer stars move fast, not because of an invisible halo of matter, but because gravity in that ultra-low acceleration environment is inherently stronger than Newton thought. MOND predicts the rotation curves of hundreds of galaxies beautifully, without requiring a single speck of dark matter.
So, if Molandi mathematically solves Vera Rubin's flat curves perfectly, why is the vast majority of the scientific community still digging underground searching for WIMPs? Why isn't MOND the standard model?
Because the universe is much more than just individual spiral galaxies. When we look at larger cosmic scales, MOND begins to struggle. It has a very hard time explaining the dynamics of massive galaxy clusters, like the ones Zwicky studied.
I see.
More importantly, MOND struggles to accurately predict the microscopic temperature fluctuations in the cosmic microwave background radiation, which dark matter models predict with astonishing precision. Dark matter also provides the essential framework for how the cosmic web of galaxies formed over billions of years. MOND simply doesn't scale up to the whole universe cleanly.
But wait, the dark matter paradigm is suddenly facing a massive crisis of its own right now as we record this, and it's coming from the James Webb Space Telescope.
Yes, the JWST anomalies are currently sending shockwaves through cosmology.
The standard dark matter model relies on hierarchical formation. Dark matter slowly clumps together over billions of years, creating gravity wells that pull in hydrogen, forming small stars which merge into small galaxies, which slowly crash together over eons to form massive galaxies like our Milky Way. It's a slow bottom-up process.
That is the core prediction of the cold dark matter model. But JWST was designed with infrared sensors specifically to look back in time, to the very dawn of the universe, just a few 100 million years after the Big Bang.
And what is it seeing?
According to the dark matter timeline, JWST should only see chaotic, tiny proto-galaxies. Instead, it is discovering massive, fully formed, highly structured spiral galaxies existing impossibly early in cosmic history. They are too big, too mature, and too numerous. They seemingly formed far faster than dark matter hierarchical models allow.
It's like digging into the ruins of ancient Rome and finding a fully functional nuclear submarine. It completely breaks the timeline. And MOND advocates are pointing out that modified gravity actually predicts rapid galaxy formation much better than dark matter does.
Well, we must remain entirely neutral in this debate, observing it as impartial guides. The scientific community is actively fighting over this data right now. Some argue we just need to tweak how we model star formation in the early universe, while others believe JWST is showing us the cracks in the dark matter paradigm.
It's fascinating.
We are living through a scientific revolution, watching the paradigm tremble in real time.
So what does this all mean? Just sit with that thought for a moment as you listen to this. Whether the universe is permeated by a ghostly sea of axions, an ancient swarm of microscopic black holes, or whether the very fabric of gravity behaves in ways we don't fully comprehend, the undeniable truth is that the visible world is an illusion.
Absolutely.
The invisible architecture of the cosmos is silently spinning the galaxies right above your head. It is an awe-inspiring, humbling realization. But as profound as dark matter is, it is only the glue. We have explored the force pulling everything together. Now we must shift our gaze to the force tearing everything apart.
We have to confront dark energy.
Exactly. And to do that, we have to return to the mind of Albert Einstein.
Let's step back to the year 1915. Einstein publishes his general theory of relativity. It's a monumental achievement. He fundamentally rewrites our understanding of gravity. It is no longer just an invisible tether pulling objects together. Gravity is the actual warping of the four-dimensional fabric of space-time.
Right.
As the physicist John Wheeler famously summarized, in mass tells space-time how to curve, and curved space-time tells mass how to move.
It's a beautiful, elegant geometric theory, but when Einstein took his shiny new equations and tried to apply them to the universe as a whole, he ran into a terrifying mathematical reality. The math demanded that the universe be dynamic.
The problem was gravity. If you have a universe filled with massive objects, stars, gas, galaxies, their mutual gravitational attraction will pull on every other object. If the universe is static and sitting still, gravity will inevitably drag everything together until it all collapses in a catastrophic crunch.
Just a giant implosion.
Yes. Einstein's equations clearly showed that a universe with mass cannot be static. It must be either currently expanding or actively contracting.
But Einstein didn't want a moving universe. The overwhelming philosophical consensus of the early 20th century was that the universe was eternal, static, and unchanging. The stars were fixed in the firmament. That was his comfort zone.
He was deeply influenced by Mach's principle and the prevailing philosophical prejudices. He couldn't accept a dynamic universe. So in 1917, he did something highly unusual for him. He tampered with his own perfect equations.
He introduced a fix.
He added a new mathematical term to the stress-energy tensor, represented by the Greek letter lambda. He called it the cosmological constant.
Explain the mechanism of lambda. How does adding a letter stop the universe from collapsing?
Lambda represented an intrinsic, uniform energy density assigned to empty space itself. It acted as an anti-gravitational force, an outward push inherent in the vacuum. By very carefully tuning the exact value of this cosmological constant, Einstein could perfectly balance the scales. The inward crush of gravity from the stars was exactly canceled out by the outward push of the vacuum. The result was a universe mathematically forced to remain still, eternal, and perfectly static.
He essentially invented an invisible force purely to save his philosophical worldview. But the universe doesn't care about our philosophy. Just 12 years later, in 1929, Edwin Hubble completely shattered the static universe.
Using the massive Hooker telescope on Mount Wilson, Hubble observed distant galaxies and analyzed their light. He discovered that the light from almost every galaxy was redshifted. As we discussed with Zwicky, a redshift means the object is moving away from the observer.
But Hubble found something more profound than just random motion. He discovered a direct relationship. The further away a galaxy was, the faster it was moving away from us. A galaxy twice as far away was receding twice as fast.
Which means it wasn't just galaxies flying through pre-existing space. The fabric of space itself was expanding, carrying the galaxies along with it like raisins in a rising loaf of bread.
Oh, I love that analogy.
The universe was not static. The dynamic universe Einstein's original equations predicted was real.
Einstein was reportedly devastated by this. He abandoned the cosmological constant entirely, allegedly calling it his greatest blunder. He realized he had possessed the mathematical tool to predict the expanding universe a decade before Hubble discovered it, but he let his prejudice blind him.
The historical record of this period is fascinating. In our sources, We have a recently translated 1931 paper by Einstein, meticulously analyzed by researchers Forte and McCann. It offers a rare glimpse into Einstein's thought process immediately after Hubble's discovery.
What does it show?
In this paper, Einstein is actively trying to construct a model of the universe without the cosmological constant.
He's throwing it in the trash.
Exactly. He writes, one must ask whether one can account for the facts without the introduction of the lambda term, which is in any case theoretically unsatisfactory. He embraces the dynamic universe. Using the framework of Alexander Friedmann, Einstein's 1931 model envisions a universe that begins with an initial impulse of expansion. However, without lambda to push outward, the collective gravity of the universe acts as a brake. The model predicts that the expansion will eventually slow down, halt, and reverse, leading to a cosmic contraction, a cyclic universe.
It's worth noting the humanizing aspect of this translated paper. The researchers point out that Einstein actually made some mathematical errors in this paper. He stumbled while calculating the radius and age of the universe based on the density of matter, getting numbers that didn't align with the data.
Even Einstein made math errors.
Yeah. You can still see the original chalk calculations for this exact model preserved on a blackboard at Oxford University. But the philosophical takeaway is Occam's razor. Einstein felt a bad conscience about inventing an arbitrary fudge factor like lambda. Once the static universe was disproven, cutting lambda out of the equations was the most scientifically rigorous, logical thing to do.
What's fascinating here is Einstein's logical decision to kill the cosmological constant was entirely reasonable in the 1930s, but it robbed him of predicting what might be the most shocking scientific discovery of the modern era.
Because 70 years later, the universe proved that Einstein's fudge factor was actually the most profound, powerful number in all of physics.
This brings us to the cosmological watershed moment of 1998. Two highly competitive independent teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, including Brian Schmidt and Adam Rees, were racing to answer a fundamental question. Exactly how fast is the universe's expansion slowing down?
Wait, everyone still assumed it was slowing down.
Absolutely. The logic was inescapable. The Big Bang was the initial push driving everything apart. But the universe is filled with gravity. The collective gravitational pull of billions of galaxies must be acting like a giant brake pedal, fighting the expansion, slowing it down.
That makes perfect sense.
The only question was, is there enough mass to eventually stop the expansion entirely and trigger a big crunch? Or will it just coast forever, slowing down infinitesimally but never stopping? To measure this deceleration, the teams needed to look back in time at extremely distant objects. They needed incredibly precise distance markers.
They needed standard candles. Let's explain the mechanism of how they measured this, because it's brilliant. They used a very specific type of exploding star called a Type Ia supernova.
A Type Ia supernova occurs in a binary star system where a dense, dead star called a white dwarf is locked in orbit with a companion star. The white dwarf possesses immense gravity and it slowly siphons gas off its companion.
It's a vampire star.
Yeah, exactly. It steals mass, slowly growing heavier. But the laws of physics impose a strict limit on white dwarfs, known as the Chandrasekhar limit, which is approximately 1.4 times the mass of our Sun.
The moment the white dwarf steals enough gas to cross that exact mass limit, the core cannot support its own weight. The star collapses and triggers a runaway, catastrophic thermonuclear detonation.
Because every single Type Ia supernova explodes at that exact same mass threshold, the physics of the explosion are virtually identical every time. They ignite with the exact same intrinsic, absolute luminosity.
Perfect standard candle.
They're the ultimate standard candle. If you see a Type Ia supernova in a distant galaxy and it looks faint, you know exactly how far away it must be based on how much the light has dimmed over distance. By measuring its distance and simultaneously measuring its redshift to see how fast it's moving, you can chart the expansion rate of the universe over billions of years.
I want to try a new analogy to capture the sheer mind-breaking shock of what these two teams found in 1998. Imagine you are standing in an open field and you throw a baseball straight up into the air as hard as you can. It rushes upward, but immediately the gravity of the Earth starts pulling on it. You watch it slow down, slower and slower as it fights gravity. If you threw it with impossible strength, reaching escape velocity, it might leave the atmosphere and coast into deep space, but it would always be gradually slowing down, dragged by Earth's gravity. What Perlmutter, Schmidt, and Rees observed in 1998 is the equivalent of watching that baseball slow down as it reaches the clouds, hover for a moment, and then suddenly, impossibly, hit an invisible thruster and rocket upward, accelerating faster and faster out into the solar
It
system.
was a discovery that fundamentally broke our understanding of cosmology. The data was undeniable. The distant supernovae were dimmer than they should have been if the universe was merely coasting. They were further away than predicted. The expansion of the universe was not slowing down.
The brakes weren't working.
The brakes weren't working, the expansion was actively accelerating. The galaxies were being pushed apart faster today than they were a billion years ago.
The teams were terrified of their own data. They spent months trying to find errors, thinking maybe cosmic dust was dimming the stars. But it was real. Some unknown, ubiquitous force was overpowering the combined gravity of the entire universe, actively tearing space apart. Cosmologist Michael Turner coined the term dark energy to describe this mysterious engine of acceleration.
And here we face the ultimate question: what exactly is dark energy? And the most widely accepted answer brings Einstein's greatest blunder back from the grave. Dark energy appears to behave exactly like the cosmological constant lambda. It acts as an intrinsic, fundamental property of the vacuum of space itself.
Which means empty space isn't actually empty.
Far from it. When we look at empty space through the lens of quantum mechanics, we discover that the vacuum is incredibly active. It is a bubbling, chaotic quantum soup.
Virtual particles.
Yes. The Heisenberg uncertainty principle allows for pairs of virtual particles and antiparticles to constantly pop into existence out of nothing, briefly interact, and immediately annihilate each other in fractions of a microsecond. This isn't just theory. We can measure this vacuum energy through phenomena like the Casimir effect, where two uncharged metal plates pushed extremely close together in a vacuum will actually experience a physical force pushing them together due to the exclusion of certain quantum fluctuations between them.
So the vacuum has a baseline energy, and this creates a terrifying feedback loop. If dark energy is a property of space itself, then as the universe expands, it creates more space. More space means more vacuum energy. More vacuum energy pushes the universe to expand even faster, which creates even more space. It's a runaway cosmological train.
Yes. But as elegant as that sounds, combining quantum mechanics with cosmological gravity creates what is widely considered the greatest embarrassment in modern theoretical physics.
The 10 to the 120 problem. We have to dwell on this because it's not just a rounding error. It is a catastrophic failure of our math.
It is profound. When quantum physicists sit down and calculate exactly how much vacuum energy should be generated by all these bubbling virtual particles, they get a specific number. When cosmologists look through telescopes and measure the actual acceleration of the universe to determine how much dark energy is present, they get another number.
And they don't match.
The quantum calculation is larger than the cosmological observation by a factor of 10 to the power of 120.
That is a 1 followed by 120 zeros. To put that in perspective, there are only about 10 to the 80 atoms in the entire observable universe.
If the quantum calculation were accurate, the density of dark energy would be so overwhelmingly powerful that it would have ripped the universe apart fractions of a second after the Big Bang. Space would have expanded so violently that no two particles could ever have found each other. Stars, galaxies, planets, and humans could never have existed.
So the math is just wrong.
The discrepancy is so vast, it has been called the worst theoretical prediction in the history of physics. It clearly signals that our two most successful frameworks of reality, general relativity for the macro and quantum mechanics for the micro, are fundamentally incompatible when applied to the vacuum of space.
So if it isn't a constant vacuum energy, if the cosmological constant is wrong again, what is the alternative?
The primary alternative is a dynamic theory called quintessence. Unlike the cosmological constant, which is rigid and unchanging, quintessence proposes that dark energy is an evolving scalar field that permeates all of space, somewhat analogous to an electromagnetic field.
Okay.
Because it is a dynamic field, its strength and properties can change over cosmic time. Billions of years ago, the field might have been weak or even attractive. Today, it is repulsive. Billions of years from now, it could grow infinitely stronger, or it could decay and reverse itself.
Which means the ultimate fate of reality, the way the universe ends, depends entirely on the true nature of this dark energy. How does this dictate our cosmic demise?
Let's look at the thermodynamics of the endings. If dark energy is indeed the cosmological constant, a uniform property of space, then the universe faces the big freeze.
A big freeze.
The accelerated expansion will continue indefinitely, pushing galaxies further and further apart. Eventually, the expansion of space between us and distant galaxies will exceed the speed of light. The light from those galaxies will never be able to reach us.
We'll be alone.
The night sky will go completely, utterly dark. Over trillions of years, The stars will exhaust their fuel and die. Galaxies will dissolve into the void. The universe will become a vast, expanding ocean of freezing darkness, approaching absolute zero, completely devoid of structure or energy transfer.
A quiet, endless freezing fade into nothingness. But what if it's quintessence?
If dark energy is a dynamic field, and its repulsive power increases over time, a scenario known as phantom dark energy, we face a far more violent apocalypse, the Big Rip.
The Big Rip.
In this model, the acceleration of space doesn't just push galaxies away from each other. The repulsive force actively overpowers gravity on smaller and smaller scales. First, it rips apart galaxy clusters. Then it strips the stars away from individual galaxies.
Oh, wow.
As the field grows stronger, it overpowers the gravity of solar systems, flinging planets away from their dead stars. Finally, in the very last fractions of a second of time itself, the expansion of space overpowers the strong nuclear force, tearing the very atoms themselves to shreds.
It is a profoundly heavy thought to carry. The universe either freezes to death in the dark or shreds itself into subatomic confetti. But as we peer into this terrifying, infinitely distant future, we can turn to the final theories of two of the greatest minds of our era, Stephen Hawking and his longtime collaborator Roger Penrose. They dared to mathematically explore the boundaries of time itself.
Hawking spent his entire career attempting to bridge that massive gap we discussed, unifying the crushing macrogravity of general relativity with the chaotic microrules of quantum mechanics. He did this primarily by studying the extreme environments of black holes. Early in his career, he proved the area theorem, demonstrating that the event horizon of a black hole can only increase, never decrease, a macroscopic rule, beautifully confirmed in recent years by the LIGO detection of gravitational waves from colliding black holes.
But his most famous discovery involved adding quantum mechanics into the mix. Hawking radiation.
Yes, Hawking realized that the quantum vacuum fluctuations we discussed, those pairs of virtual particles bubbling into existence, must also happen right on the very edge of a black hole's event horizon.
The point of no return.
He calculated that occasionally a pair forms right on the boundary. One particle falls into the black hole while the other escapes into space. The escaping particle becomes real radiation, stealing a tiny fraction of the black hole's mass. Because of this Hawking radiation, black holes aren't completely black. Over immense, unimaginable timescales, they slowly evaporate and leak their mass back into the universe.
But towards the end of his life, Hawking's focus shifted away from black holes and toward a massive philosophical crisis in cosmology, the fine-tuning problem. Why is our universe so perfectly balanced? Like you said earlier, if dark energy had been just a tiny fraction stronger, the universe would have blown apart. If it was slightly weaker, gravity would have crushed it back into a singularity. It feels suspiciously like the dials of the universe were precision engineered for life to exist.
The standard cosmological answer to the fine-tuning problem relies on eternal inflation, which naturally generates a multiverse.
A multiverse.
The theory suggests that the Big Bang wasn't a singular, unique event. Instead, there's a background state of space that is constantly, eternally inflating at breakneck speeds. Within this rapidly expanding ocean, certain regions randomly slow down and stabilize. These stable pockets become independent universes, bubbling into existence like steam bubbles in a boiling pot of water.
And because inflation is eternal, there are an infinite number of these pocket universes.
Exactly. And in an infinite multiverse, the laws of physics and the value of dark energy might be entirely different in each bubble. The vast majority of these universes might be sterile voids or instant collapses.
But just by chance.
By pure statistical inevitability, in an infinite set, there must be a universe where the dials are set perfectly for carbon-based life to evolve. We aren't special. We just inherently find ourselves in the exact bubble that allows observers to exist.
But Hawking fiercely rejected this. He believed that if you rely on an infinite, chaotic, fractal multiverse where literally everything that can happen does happen somewhere, your theory loses all scientific predictive power. You can't test a theory that just shrugs and says everything is possible.
He found it deeply unscientific. So in 2018, just days before he passed away, Hawking submitted his final paper, co-authored with Thomas Hertog, titled A Smooth Exit from Eternal Inflation. It was a brilliant attempt to tame the infinite multiverse.
How did they do it?
They utilized incredibly complex mathematics derived from string theory and the holographic principle.
The holographic principle, where the 3D volume of a space is mathematically encoded on its 2D boundary.
Exactly. By applying these holographic techniques to the origin of time, Hawking and Hertog proposed that the multiverse is not an infinite chaotic fractal of wildly different physical laws. Instead, the mathematical structure of the quantum boundary restricts the multiverse to a finite, much simpler set of universes that are all fundamentally similar to our own.
Oh, that's interesting.
In Hawking's final vision, the fine-tuning of dark energy isn't a miraculous freak accident in an infinite sea of chaos. It is a natural, mathematically restricted outcome of the universe's holographic origin. Our existence, our perfectly balanced universe, becomes a logical, predictable consequence of the physics.
Here's where it gets really interesting. It's a comforting thought, finding order in the chaos at the beginning of time. But while Hawking was looking for order at the very beginning, his colleague Roger Penrose was looking at the absolute, infinitely distant end. Penrose developed a theory called conformal cyclic cosmology, or CCC.
Penrose forces us to confront the extreme mathematics of the Big Freeze. Let's fast forward trillions upon trillions of years into the future.
Okay, we're way into the future.
The universe has expanded exponentially due to dark energy. The last stars have burned out. The galaxies have dissolved. All normal matter has decayed. The only things left are supermassive black holes. But eventually, even they succumb to Hawking radiation.
So they fade too.
Over timescales that defy human comprehension, every black hole slowly evaporates away, converting all its mass into faint photons of light and gravitational waves.
So the end state is a universe that is infinitely vast, infinitely cold, and completely empty of mass. There is no matter left, just massless radiation drifting forever.
Precisely. And here is Penrose's brilliant mathematical revelation, which relies on conformal geometry. In physics, mass is what gives the universe its scale. Massive particles, like electrons or atoms, act as physical clocks ticking through time, and they act as rulers measuring distance.
Because they have a rest mass, they experience time.
Yes, but photons of light are massless. As they travel at the speed of light, they do not experience time, and distance contracts to zero for them. If the universe eventually contains no mass whatsoever, then the very concepts of time and distance lose all mathematical meaning.
Wow.
Without mass to measure scale, a universe that is infinitely large is geometrically indistinguishable from a universe that is infinitely small.
Wait, let me make sure I'm grasping this. Because there is no matter left to act as a ruler, the universe forgets how big it is.
Mathematically, yes, the metric loses its scale.
Yeah.
Penrose showed that the geometry of a cold, infinitely expanded, empty universe without mass is completely conformally identical to the ultra-dense, incredibly hot singularity that existed at the exact fraction of a second of the Big Bang.
So the infinite freezing end state of our universe is mathematically indistinguishable from the explosive, fiery birth state of a new universe. The end of our reality directly triggers the Big Bang of the next. It's not a timeline, it's a circle.
It is an eternal cycle, a cyclic cosmology. When the universe loses its mass, a new cycle, or what Penrose calls an eon, begins. It is an endlessly repeating chain of cosmic breaths.
That is beautiful.
Penrose and his team have even controversially claimed to find evidence of this. They searched the cosmic microwave background for what they call Hawking points. The theory suggests that the incredibly violent evaporation of supermassive black holes at the very end of the previous eon would have sent massive shock waves of energy into the future, leaving faint, ghostly circular scars hidden within the temperature variations of our own universe's ancient light.
That is the ultimate relaxing symmetry. To lie under the stars, feeling small against the dark, and realize that the terrifying cold end of everything isn't a final death. It might just be the exact mathematical mechanism that breathes life into a brand new beginning, an eternal chain of existence.
It fundamentally rewrites our relationship with time and the void.
Let's summarize the immense, invisible journey we've taken today. We are floating in a universe where the entire visible world, every star you can see, every galaxy we can photograph, every atom in your body, is just a 5% sliver of reality.
Just 5%.
We exist as glowing anomalies in a cosmic jar dominated by the unknown. Dark matter acts as the silent gravitational scaffolding, the invisible web holding galaxies together, discovered through the impossibly fast spinning anomalies of Vera Rubin and the coma cluster velocity observations of Fritz Zwicky.
Yes.
Meanwhile, dark energy acts as the great repulsor, an active driving engine stretching the fabric of space toward infinity, born from Einstein's greatest blunder and confirmed by the shocking acceleration of exploding supernovae in 1998. And our greatest minds, from Einstein to Hawking to Penrose, have slowly, painstakingly, mathematically peeled back the veil on this invisible architecture.
But I want to leave you, the listener, with a final, provocative thought to mull over, one that stretches beyond the limits of this deep dive.
Let's hear it.
What if we are looking at this dark universe entirely wrong? What if dark matter and dark energy aren't stuff or particles at all? In the cutting-edge realms of M-theory, string theory, and holography, there's a concept that our entire three-dimensional reality might just be a flat projection residing on a boundary within a higher dimensional space, often referred to as the bulk.
Like a 3D hologram projected from a 2D surface.
Yes. And crucially, in these models, while electromagnetism and the nuclear forces are permanently trapped on our 3D projection, gravity is not.
Gravity can escape.
Gravity is the only force theorized to be capable of leaking across dimensions, rippling through the bulk. Therefore, it is entirely possible that the invisible mass we stubbornly call dark matter and the repulsive vacuum energy we call dark energy are not missing particles hiding in our universe.
Then what are they?
They might be the gravitational shadows of massive objects, or immense forces existing in parallel universes pressing right up against our own reality from higher dimensions we simply lack the geometry to see. The dark forces pulling our strings might just be the fingerprints of the true multidimensional cosmos bleeding into our flat world.
Just let that sink in as you look up at the night sky tonight. The darkness between the stars isn't empty space. It is the most powerful, active, and mysterious force in existence. It is the scaffolding of reality, and it might just be the shadow of something vastly greater. Thank you for joining us on this incredible deep dive. Keep looking up, keep wondering, and don't forget to subscribe and like to this channel, Decoding the Dark, to continue exploring the unseen with us. See you next time in the deep dive.